Okay, well, tonight I had the misfortune of forgetting my stylus for my um, um, writing tablet at school because I am now carting that back and forth. It's not a big deal because it's only about that big and it's not like an expensive piece of equipment or anything. Um, but yeah, I forgot my stylus at school, so I am not going to be able to um, write anything by hand just on the whiteboard. I think probably my best bet is to type out everything that's here. It's going to look a little more boring. I won't be able to get diagrams quite the way that I want to, but it's better than nothing. And I did this last week too when I joined in the Twitch Blackout Day. I hadn't even realized that it was Twitch Blackout Day, and until after I had forgotten my entire writing tablet. So, eh, I would have found out anyway at some point, and then canceled the stream. But so we are waiting for the Microsoft Whiteboard to start up, and I'm also trying to start up GIMP in the background because this is a very old version, but it also at least allows me to, uh, you know, type something on a blank sheet of paper, essentially. It may, in fact, even allow me to... Yeah, okay. I think we could do whiteboard just fine. Alright. So, let's turn down... Turn down Pretzel a little bit anyway. So, hi, how are you? Good evening. If there is anyone out there who would like to talk about some of the home... Oh, no. Really? Yeah, I don't get the option to change styles. Oh, that's awful. It's almost as bad as Comic Sans. Alright, well, we're just going to have to deal with it. Because I'm the idiot who forgot the stylus. Alright, so if anyone has any particular questions on homework to be done, to be helped with, please let me know. And other than that, I will start in on a couple of questions that have been coming up this week for my students, since they are starting classes in earnest and finally getting into some actual mathematics, not just the introduction to the class, but actually like what's going on in the class. So how to do stuff without actually needing a pen. Well, this will be fun. All right. All right. So one of the classes that I'm teaching is Introduction to... Nope, that's not it. So I'm teaching Calc 2 this semester, hence why I was working a bit earlier on some of the integration methods and other items like that. And tonight I'm going to be working with, what was it, topics? Yeah, that was it. Topics in mathematical literacy. So feel dirty just typing this. Really? Can't change the... I feel like... settings? Oh. Really? Alright. I mean, fine, I guess. Alright, so topics in mathematical literacy included the main topic that we are going to be dealing with tonight, which is logic. So within logic, we have a few different areas of concern. So the first thing that we're going to be dealing with is so when we talk about logical statements, these are going to be declarative sentences or what have you. Declaratives that are objectively true or false. So when you're talking about statements, you're typically talking about something like, you know, my shirt is black, or in fact, my shirt is green. Those are declaratives, and one of them was clearly true, and one of them was clearly false. So in the case of my shirt is black, this is a true statement. In the case of my shirt is green, this is a false statement. Both are statements. They are both declaring the color of my shirt. And in addition to statements, we also have of course, I don't have my teaching notes out. Why would I do that? That's... Nope. Okay. So, within logic, we have statements. These are going to be things like, again, okay, and in addition to this, we have things that are not statements would be stuff like opinions, interrogatives, basically any sort of question. Commands or demands. And exclamations. So, in the case of, for instance, apt for today, in the case of everyone's favorite Keanu line from the first Matrix movie, whoa, That is an exclamation, and that is not going to be a statement. It has no true or false value. Something that is a command like, hey, get me that pen, also has no true or false value that goes with it. Same with interrogatives, so if you ask, what color is my shirt? Or even, is my shirt black? That by itself is not, again, is not true or false. It is simply a question. And opinions like, I think my shirt is darker than that shirt over there, or I think my shirt is cooler than that shirt over there, that would not be a statement due to the fact that it is an opinion. So, in addition to the really awesome stuff like this, we also have some tough mathematical truths that were found out when all of this logic mathematics was being worked out. Hilbert, David Hilbert from Germany, had some ideas that in the early 1900s there were going to be a certain number of questions in mathematics, I believe 23, that needed to be answered by the end of the 20th century. So they needed to answer all of these particular questions by the end of the 20th century in order to continue really understanding and doing mathematics. Hey, how's it going, Superbrain? Why, thank you. I agree. So, nope. Where's the... there we go. So Kurt Gödel was a mathematician who started answering one of David Hilbert's questions, or doing research on, which was something to the effect of, are all mathematical, or can mathematics be put on a firm logical framework? Put into a firm logical framework. And Gödel eventually came out with the idea that no, actually, mathematics cannot be put on a firm logical framework, because unfortunately there are some questions in mathematics which will be unprovable. One example that he chose to use for this was if you use the statement, because it is a statement, this statement is false. So he found that if you try and use this statement is false to, even not necessarily literally this, but there are some mathematical questions within the field of mathematics which boil down to something that's almost exactly identical to this, where it says that this statement is false. If you assume that it's true, then it says that this statement is false. So this is going to lead to a contradiction, because the statement can't be false if you just said it was going to be true. Okay. And if you assume it is false, then we end up getting this statement is not false, which means that this statement is true, which is, again, another contradiction. So you can't actually prove this statement due to the fact that if you try to prove the statement, you end up going in this big circular logic issue. So this is a paradox, which is basically a statement that contradicts itself. So. So. Oh, right, and this is kind of important. So this ends up being called Gödel's incompleteness theorem, which now says that mathematics cannot be placed on a logical framework due to the fact that, again, there are some statements within mathematics which will be paradoxes, which will be extremely simple to just state them out loud, but absolutely impossible to prove. And that's really too bad, but very interesting at the same time. So, oh, and one of my students came up with this one. Another not statement would be suggestion. Sometimes it could be a statement, but a lot of times suggestions are opinions. So it kind of falls under the category, or at least most of the time falls under the category of opinions, and then you can just go with that. So there are also compound statements, which are two or more statements linked, that's a better word for it, by connectives. That's off the page, isn't it? Yeah, only a little. Alright, that's fine. Yeah, I don't typically adhere to the same teaching philosophy that my coordinator does for this course. She's like very cut and dry, just like get this stuff out and then just move on. And I'm like, no. So I've been intentionally inserting little asides of, historical bits of mathematics. Nothing about necessarily, I did mention Gödel's incompleteness theorem. I did not go into it besides like what I just did here. And I did the nice little aside of the fact that, Gödel, as well as many other Jewish mathematicians and scientists and academics in general, were pushed out of Germany by the Nazi regime. And then after moving to America, Gödel was one of the, luckier people to escape to come to America. And he lived up the street from a physicist friend of his. They would always walk to Princeton together and discuss mathematics and physics on their way. And then they would, part ways, go and do their classes. And then, at the end of the day, they'd, meet up for dinner or what have you with their families and, have a pretty decent time. And, his Kurt Gödel's best friend was one, Albert Einstein. So a number of the students went, like, hey, there's a connection. So it gets into their heads a little bit that these are important, like, human stories that yeah, I mean, who wouldn't want to argue physics with Albert Einstein? Even if you didn't understand it, let's just talk. So, yeah, two compound statements, or two or more statements that are linked by connectives are going to get you compound statements. Well, then what are connectives? These are linking words in mathematics. They have very specific meanings. So the first one is called the conjunction between two statements. And this is referred to usually as the AND statement. And also, the proper notation for this, if we let our statements be abbreviated, typically they're going to be abbreviated by, we start with P, which generally means premise. So it's going to be some sort of statement that we make that is going to be part of a larger structure. Usually what's considered an argument, which we'll define in a little bit. So P, Q, R, S, and T, and you can keep going from there, can be your statements, and they can be abbreviated to be that, so that you don't have to keep writing them over and over again. Or you could decide instead to label them as like P sub 1, P sub 2, P sub 3. And that makes it a lot easier to just list out a whole bunch of them. Then you don't have to worry about running out of letters. Right, that's a good idea. All right. Let's just do that. All right. So typically we're going to do some sort of notation like this. Now normally this would actually be in line with the other two, not a caret like you're exponentiating this, but I'm not using the proper Unicode stuff, so this is just going to have to suffice for now. I guess I could actually pull up the bitmap, because then I could just copy paste. That's easy enough. It's saying circumflex accent, which, again, is more like a caret than it is a... there we go. Got it. Copy. Paste. Yeah, that's going to work. Yeah, so I can manually type most I can manually type most accents that you're going to find in French. So if it is something that you could potentially have in French, I know how to do it. And sometimes other languages as well. Like I know, there we go. I know where they are. This particular one, like the let me put it this way. The Unicode for it is U plus O2C4, but I have absolutely no idea how to do that. I use Alt. I misspoke. I use Alt codes. So, you know, hold down the Alt key and type usually 3-digit code on your keypad. Yeah, the O with the umlaut is Alt 148, and that was through 2 minutes of trial, or 10 seconds of trial and error, because I knew about where O's are in this. There are some weird exceptions to that rule, so it jumps around because of language sometimes, and like, you know, I hit 147, 146, 145. We're starting to get out of O's and back into like I's. but not all of the accents are in the 140s, and I'm like, you know, in order to get like U with an umlaut, I think you need to do 128 or 129. It's ridiculous. And all the rest of the U's are in the 150s. So, like, I have no idea where half this stuff is actually coming from, but it's fun. Alright, let me put that down there. Okay. So, we got the conjunction, which is going to be and statements, which are going to be P and Q like that. We have disjunction, which are going to be or statements, which are going to be P or Q. So we're going the other way. There we go. Copy. I mean, technically it's like a V, but it's also not the letter V. So, P or Q like this. We also have the ones we're doing in my class anyway. We have the conditional, which is if then, which is P implies Q. So let's see if we actually have this one here. I know that we have. Ooh, that's awesome. We do actually have some integration and stuff like that, so that's helpful. Here we go. Arrows. No, I don't want harpoons. There we go. Select and copy. Alright, so P implies Q like this is going to be this double arrow that's pointing out toward Q. And biconditional, which is some stuff followed by if and only if, followed by some more stuff. And this is going to be P with a double-headed arrow. P implies Q. Well, right. And what this one actually means... no, bad idea. Okay. What this one actually means... is P... Oh no. There we go. P implies Q. Alright, I'll come back to that. And... Yep. Oh, okay. Nope. Yeah, not here. I could do it, but this, like, pseudo Comic Sans stuff is driving me nuts. No, hey, that's fine. It's perfectly fine. Alright, so we'll do and here for now, and then Q implies P, like that. And then we'll switch out and for the actual accent once I go back and find it again. Hooray! Got a whole bunch of Russian accents. It's great. And order of operations does actually apply here. Just that the order basically says that these implications come first in the order of operations, followed by the AND statement after that. You don't have to put parentheses, although sometimes that's a better organizational tool. So you can do that if you feel like it or not. Doesn't really matter. Alright, then... There are also other connectives which we don't use in my class, which include NAND, NOR, and XOR, which is exclusive OR. NOR is going to be not OR, and NAND is going to be not AND. I guess technically it's not or not. Like not A or not B. So exclusive OR is P and not Q or not P and Q. So the exclusive OR is generally what you think of when you hear somebody say either or, because it's one or the other. But the issue with mathematics is that it's not exactly... quite possibly. Oh, man. Well, this is why. We're not doing this in my class. Yeah. Yep. Yeah, I think you're right. Yep. Alright, A nor B is going to only work when both are false. Trentonad. Greetings, good evening. So not exactly, but I can help you work through some of your problems and try to help you understand something more deeply. Yep, so that is going to be at Superbrain, thank you. Right, and it is interesting to note, right, the negation does mean that this thing is going to be the same as not P or not Q. And this one's going to be not P and not Q. So, Trentonut, if you're still here, feel free to drop that into the chat, and I can help you understand the concept better. Right, so then this stuff gets into, like, what is negation? Which, what did I even say? We were talking about it in my class today. What did they say? Ew. I got some really bad pictures today. Well, I mean, you don't have to be perfect at anything, right? This is... I'm just happy to talk. Guacosa TV, welcome. Thank you very much. Well, I can attempt to fill that void in your life with some mathematics. So if there's anything you want to talk about, you know, any specific topics or anything like that, I am game. This is just me riffing and basically rehashing my lecture from the last couple of days so that, you know, I can sort of decompress and I'm essentially doing an autopsy on what I did in class in my head now. And so if I'm talking to you all... Oh no, I'm sorry. I mean, you know, good news, there's always the on-demand video, so... I am under no illusion that people are going to 100% watch my stuff, you know, in their free time. But hey, I know realistically there are people who actually do, and I thank you very much. Um, so, with negation, this is the opposite of a statement, so we did something earlier like if P is... Oops, no. If P is, you know, my shirt is black, then not P. usually denoted by a tilde, although there is also another symbol in the character map. And I did see it earlier. Let's hope it's readily accessible. Not so much. Okay. Ooh. It's no good. Ah, there we go. Yeah, it's like right in the... It's right on the top row. This is cool. Or not row, but in the top page. So it's this line with a little bit of a bar next to it. That. Guess we could say that this is like equal to, not P. Right, these are going to be identical statements, so my shirt is not black, which also, interestingly enough, right, gives a lot of wiggle room. So if a declarative is saying something very specific, then the negation of that declarative is going to be a very widespread, very large sort of statement. So my shirt is not black. It gives it a lot of different colors that it could be. All right, and this can lead us into quantifiers. Okay, so descriptors of like numbers of objects is going to be some sort of quantifier. We could, for instance, do something like, all right, there are two different kinds. Universal quantifiers describe some sort of property of like everything. Let's go like that. Let's stretch this a little bit. Maybe. Close enough. And then we have existential. I lost. So, existential quantifiers are those things which describe properties of some things, not all things. So a lot of existential quantifiers are going to be like, you know, some people go to the park, or some people went to the park today. Universal quantifier would be like, everybody I don't even know. Oh, Superbrain, you are in trouble. So there, when I was in college, or rather, I guess when I first got like, uh-oh, I'm dropping frames. Okay. So when I was in, no, I was in college. When I was in college, somebody decided to be funny, and I don't know where this came from. It goes back a long way, I'm sure, and it wasn't at my college that it was invented. But they said they were in philosophy at the time, this particular person, and they were like, yeah, we learned about this game. It's called existentialism. Every time that you well, now that you hear the rules, you are playing. Congratulations. Um, Every time that you realize that you are playing the game, you now have to say, I lost. It was kind of interesting. We did this at a summer camp one year, and it just went in waves across the entire, like, all of the camp staff. We were just like, oh, I lost, and everybody's like, ah. So I figured out at one point that the only way to win is to be in a constant Zen-like state of knowing that you are playing the game. Yeah, most people call it just the game because they don't know it by its technical name, existentialism. um, so anyway, congratulations, you are now playing the game. Uh, so I stayed in a like Zen-like state of knowing that I was playing the game for about a week. And it was like this weird sort of thing. Everybody's going, "Oh, I lost." And then they look at me and I'm like, "I already knew." And they're like, "What? How is that even possible? You can't do that. You have to like it's upon the realization that you are playing the game." So, when you realize, when you have that moment in your brain that goes, that's when you have to say it out loud. So, like I said, I just kind of stayed in this state of knowingness for almost an entire week, and it was a really fascinating experience. And then I just kind of let it go well, no. Then I accidentally slipped at some point and forgot, and then somebody else said, "Oh, I lost." I'm like, "Thank you." I agree. Oh, goodness. Anyway. Yeah, it was a lot of weirdness, but it was fun. All right. So quantifiers, we got descriptors of numbers of objects. Universal are going to be everything. Existential are going to be some things. Again, everything is going to be like, all people uh, had their heartbeat today. I don't know, at some point. And there's a lot of other things that you can do with this. There was a good one that was used in philosophy, which was like, actually we'll update that, right? So we could have two statements here, for example, all people are mortal, and some people drove cars. So this is one universal and one existential quantifier for two statements. Where that can go is that you could start talking about logical argumentation. So in logical argumentation, you have arguments, which are going to be a series of one or more premises. Nope. There we go. A series of one or more premises that yield exactly one solution. Okay, well, what's a premise? It is going to be a statement, which again is a declarative that must be binary, true or false. It's a statement that supports a particular conclusion, whatever that might be. And then what is a conclusion? Is going to be a statement that the author is trying to convince you is true. See, did I forget anything there? Yeah, that's fine. So one thing that we can do here is say, like, the two premises that we might take in this are that all people are mortal, and some people drove cars. So everyone who drove a car is mortal. So one of the ways in which we can kind of examine this to determine whether this is actually an argument that is correct. Actually, it's not correct. What's the proper word there? Not logical, not other thing. Valid. Yeah. So a valid argument is one that just the conclusion follows from the premises, and that's it. It doesn't actually need to necessarily be true, it just needs to actually follow. When it's sound, that's when it's valid and also true. So one of the ways that we can make this happen, or one of the ways that we can check this one up here and to figure out whether it's valid and whether it's sound, is that we can do what is called an Euler diagram. Which is sort of like a Venn diagram, but not really. So an Euler diagram is specifically looking at the okay. Oh, well, I can change the color. That's nice. Slightly. Might be slightly better just to change these up a little bit. So when we're talking about argumentation, an Euler diagram is going to be something that I can't do this, can I? Nope, because I. Hooray! Let's see, Shift. Nope. Control. Nope. Alt. Nope. Welp. That didn't work. It's too bad. Can't actually use one of those things. Alright. It's really great that I don't actually have I literally don't have a way to do this now. Hooray. Alright, let's try See if this at all works. Okay. All right, so one way to do this is to sort of works. Label your individual portions of your diagram with things like this. So we have here the group of mortals. So with the group of mortals, we have okay. Ooh. I'm using a mouse, but I'm using Microsoft Whiteboard, which I don't recommend. It's actually pretty good for like hand drawing stuff, but that's gonna be about it. So normally you start out with something that looks like a Venn diagram. So you got two circles that end up having this overlapping section. And then you label each part. Then you say, based on the premise that's given, so all people are mortal, we can say that these are, all people are going to be a subset of mortals. So all people are mortal means that people can go on the inside here, and mortals can be the outer headline here of the big orange circle. All right, and then here, some people drove cars means that within the group of people, there is also a subset. Actually, let's just use another one of these, right? So this is perfectly valid. Within the people, there is a subset who drove cars. It's not gonna, no. Right there. It's great. Man, that's worse. So, yes. So, in this particular case, right, it doesn't really say anything about other. So we would actually need a another statement that says, like, only people drive cars or something like that. So technically, everybody's favorite, this is going to look something like this. Oh man, nope. Bad idea. Yeah, you're going to have something like this where you do have some overlap, but not necessarily yeah, so there isn't this is not necessarily a subset of people. So as the argument state up above, everyone who drove a car is mortal appears to be a false statement. So that would be not actually valid, because here there are people, or there are mortals who are not people who drove cars. There are also potentially not mortals who drove cars. So the problem with this set of statements is that, oh, yeah, thank you. Nah, didn't do anything. Oh well. Um, nah. Alright, anyway. Oh, wait. Haha. There we go. Alright. It's horrible, but it can work. Right. There we go. Well, thank you. Well, it's the thing, right? It's like, you don't have to be an expert on something, you just have to have good ideas. Anyway, yeah, so this technically, you do have all these other individual possibilities that would tell you that, okay, some people drove cars. This is not going to yield that everyone who drove a car is mortal due to the fact that there are these weird outlier cases. So drove cars is still out here, technically. We still have this portion over here, which may be outside of mortals entirely. So who knows? Maybe there are some Greek gods driving around on cars. But this would be an indication that we need to clarify the argument and possibly put in some more premises or some more caveats to those premises in order to make sure that it is, in fact, valid. Oh, right. So, yep, drop that. There we go. So one of the ways to do that is to say, okay, only people can drive cars. Now, this negates the possibility that there are some animals who can actually drive a car, but I think we can probably agree that that is a reasonable assumption for most cases. So in this case, this allows us to say, okay, now we can take this and shrink it down after we get rid of some other stuff that's on here. Curses. Alright, let's just delete this. And then paste in the other, yeah. Alright, if only people can drive cars, then that means that drove cars is going to be a subset of people. And so now it is going to stick inside of people. And then, again, everyone who drove a car is mortal is now going to work. Because if only people can drive cars, people are mortal, then only mortals drove cars. Okay, that's a little better. Less fun, but a little better. People. Okay. And now this becomes a valid argument because we are driving. Yeah. So we had a third premise there. Only people can drive cars. All right, now we have to fit all of the rest of that stuff in. So the Euler diagram shrinks those circles down so that they are subsets of each other, and then that is going to that is going to allow us to draw direct conclusions which are valid and which happen to also be true. So this is a sound argument here, at least in this world. All right, so yeah. Okay, there we go. This to purple. All right, so the organization that surrounds connectives is going to be um, rather interesting, but usually what we do for connectives is that we're going to allow these connections to exist in what are called truth tables. Can't remember how to spell that properly, but two T's. So in the case of truth tables, you're going to make these Punnett squares. Again, effectively Punnett squares. They're not technically Punnett squares. Make every possible combination of true and false statements. So typically what we do is we start with like a P and a Q, and then we do some sort of compound over on the side. As we go down, we say that if we could allow P to be true, that's not going to work. And we could allow Q to also be true. Then we could allow P to be true and Q to be false. We could also allow P to be false and Q to be true. And we could allow P to be false and Q to be false as well. So we could do just about anything we want with this. We could say like P is it is Wednesday, and give me just 1 minute here. Alright, so in the case of a certain P and Q that we can use, could do something like, it is Wednesday for P, and Q, we have stream. You can imagine I would normally do we have class, but you know, it works. All right, so the first compound that we can do here is like P or crap. Or there. All right, so in the truth table, basically you're looking at all of the different possibilities that could happen. We're not necessarily going to think about what is true for today, but just, again, assume that, for instance, in the first group here, we have P is going to be a true statement, so it is Wednesday. All right, that happens to be true today, but think about it just in general. So, P is true, it is Wednesday. Q is true, we have stream. So that means that P or Q, we're really looking at, is one of these true? So in this particular case, yes, right? At least one of these statements was true, so that's going to give us a true statement overall. In the case of P being true, it is Wednesday, but Q being false, we don't have stream, so this was like last week, for example. It's still either, right? One or the other is true, and it doesn't have to be exclusive, which is why the previous one was also true. In this case, it is not Wednesday, but we do have stream. Again, this is going to be a true statement. And down here, if it is both not Wednesday and also not stream, don't have stream, then we're going to have a false statement for the or statement. Because again, it was not Wednesday and also it was not stream day. So therefore, is P or Q true? The answer is no. It's going to be false. All right, going further through, we could do P and Q. That's not the one I want. That is the one I want. For P and Q, this is going to tell us that, again, here it is Wednesday and we do have stream. So in this particular case, yes, the P and Q, are both of them true? The answer is yes, both of them are true, so that is a true statement. P and Q are true. True. All right, what about P and Q in the case that it is Wednesday, but we don't have stream? Well, it's going to be a false statement because of the fact that P is true and Q is false. Are P and Q true? The answer is false, right? No, they are not. Similarly for all of the rest of them, right? If it is not Wednesday and we do have stream, so it is Friday game night, for example, we will have another false here because again, it is not both Wednesday and we have stream. And in the final case, this is also false. It is not both Wednesday and we have stream, because in that case it is neither Wednesday nor do we have stream. So this is some random Sunday night. I have decided not to do anything. In the case of P implies Q, this is where we pull out this, this is where we pull out the conditional stuff. So if and then are going to be the words that we want to use here. So, yeah, this is always the fun one. So the implication is that if it is Wednesday, then we will have stream. So if we have two true statements, that it is both Wednesday and we have stream, then the implication that if it is Wednesday, then we have stream is going to be true. Upon the condition that it is Wednesday, we will have stream. Right? Seems reasonable so far. Wednesday comes and goes, and we do not have stream. Therefore, the implication, if it is Wednesday, then we will have stream, is going to be false, because, well, Wednesday came and went, and I was nary to be seen. Right? If I don't show up, then that implication, hey, it's Wednesday, Obi's going to be on tonight. Yeah, not so much. Right? So therefore, this is going to be false if we do not have stream on a particular Wednesday. All right, so I tried this out with my students, and let's see if you like it or not. So in this particular case, it is not Wednesday, but we still have stream. So again, this is a Friday night game night or whatever. And the question is the implication still true? That if it is Wednesday, then we will have stream. Well, it's Friday, not Wednesday. So we can't actually make any assumption about what's going on with this particular implication. Right. A Friday stream has no effect on whether or not Wednesday means we have a stream. Therefore, this is still going to be true because we have not evaluated this particular implication at all. So if it is Wednesday, then we have stream. Well, it's not Wednesday, so I don't know. Maybe we will, maybe we won't. So the implication has not been proven false, and therefore it is true. And then similarly in the last case, it's not a Wednesday and we didn't have stream, but again, that doesn't mean anything for the implication that if it is Wednesday, we will have stream, because again, nothing happened. All right, nothing happened to evaluate that statement. All right, and then the last one, the biconditional. Again, we need both P implies Q and also Q implies P. So we need to go backwards on this one. And in this particular case, what we're going to see is, again, we're going to start with Q and then look at P as the statement which has the condition of Q. So, if Q Q is true. We have stream. Then it is Wednesday. Well, we know that that may not be exactly true, but according to what we see here, that it is both Wednesday and we have stream, then the implication that if we have stream, then it must be a Wednesday, so far is holding up. With that baseline of evidence, that's all we got. All right, how about this one? So if we, no, if it is, nope. If we do have stream, then it is Wednesday. Well, Q is false in this particular case, so therefore we don't have stream. And again, the condition that we have stream is now not being used at all. So again, this has no effect. It's not being evaluated. This implication, the backwards conditional, is not going to be evaluated here. So again, we can't prove it false. It must be true, or at least it looks like it is still true. All right, this one here, if we do have stream, but it is not Wednesday, so for instance, it is Friday night stream, then here, if we have stream, then it is Wednesday, is clearly going to be false because, again, it's Friday. And again, this last one, same deal as some of the previous ones that started with a false. This is going to be true by, not H, this is going to be true by default because, again, we are not evaluating the statement, the conditional, if we have stream, then we have Wednesday. I'll get it right one of these days. If we have stream, then it must be Wednesday. So that is not being evaluated at all. All right, one more. So now we get the actual biconditional, which is, again, P is implying and implied by Q. Remember that what this is P implies Q and also Q implies P. So you remember that we had the AND statement here, P and Q. We were looking at all of the individual ones here, and then we found that only if both of these particular things were true do we actually have a true statement for the AND statement. Now, this is not going to have the same pattern because this stuff is something completely different. Equivalent, yes. So if there are two equivalent statements, like P implies Q and Q implies P, is equivalent to A biconditional Q, or wow, P biconditional Q. So then here, P with the biconditional is, again, P implies Q and Q implies P. We have a true and also a true. So the biconditional will be true in the, man, I keep wanting to do that, in this particular case. All right, in this particular case, P implies Q and Q implies P. We have a false and a true. Therefore, the conjunction between those two statements is going to be false. My fingers are like one off because the nub on the J key has been worn completely flat. Awesome. In this particular case, again, we have a true for P implies Q, but a false for Q implies P, and therefore P implies Q and Q implies P will also be false here. And in this particular case, Q implies P is true and Q implies P is true. Therefore, the biconditional will also be true there. All right, so that is our logic tables, um, or truth tables, for all of these basic connectives that we were looking at. So there are examples of making much more complicated um, compound statements. I want to use something that's here. Oh, yeah, that's a good one. Okay. Let's do this. Oh, goodness. All right. So I have one here that is P or Q, parentheses. I've told my students most of the time I'm going to put in spaces to show that, yeah, this is really what I mean in terms of the order of operations, so that you won't have to, at the very least, you won't have to do that much work in trying to decipher the order of operations. So if we want to do a truth table for this particular setup, this is a compound statement, right? P or Q and P or not Q. So for this, we'd probably want to take what we have up here and actually we just draw on it. That's fine. We take this and we copy it, paste it, and then we get rid of the stuff we don't actually want. Actually, we could just type because this is fine. All right, so we got P or Q, P or. Oh, right, I can't. I didn't. Righto. So then here. Okay. So then we're going to get P or Q and P or not Q in this end of the truth table down here. Well, so like, this isn't necessarily going to be a real statement. So in this particular case up here, if we're just using these, I don't think you'd really ever say this. So either it's Wednesday or we have stream, and also either it's Wednesday or we don't have stream. So yeah, it's really awkward to try to say like what that is. So most of the time it's not actually a thing. In this particular case, what we're doing is we're just saying like, logically speaking, what is this statement equivalent to? Is there something else that we can do to simplify this? Is there some way to, like, whatever? Really? Okay. So, realistically, we're just looking for, is there some simplification that can be done using logic? In theory, you could also work this out with algebra. So these are representative of like a pseudo addition and multiplication. They're not actually, but they're, you know, it looks sort of like that. You could also work this out using Venn diagrams and say like, you know, let's look at how these sets overlap each other, and then what are we actually looking for. Yeah, I think I can do that real quick before we leave, but alright, so let's do also not Q in here. So not Q is, again, just the opposite of what's listed under Q. So since it is true, false, this is just going to end up being false, true for not Q. P, which is the first column. Whoa. No. All right, P, which is the first column, is then going to be taken with an OR with not Q, which is this last filled in column. And again, OR, we're looking for, is at least one of these things true? So here we have P is true, and here we have not Q is false. But P or not Q is going to be true because, again, at least one of those statements is true. Next one, P is true and not Q is true. P or not Q will be true. This one, P is false and not Q is false. So P or not Q will end up being false. And here, P is false and not Q is true. So therefore, we have again, P or not Q is going to also be true there. Now, interestingly enough, right, this statement, P or not Q, according to the truth table, appears to be identical to Q implies P. That if Q, then P. Yep. All right. So then we're going to, nope. Then we're going to come over here and say, all right, what happens when we and, if we do the conjunction between P or Q and also P or not Q? So here, the conjunction between them, we have the first one, P or Q is true, and P or not Q is also true. So again, conjunction is going to be true. This is kind of the place where everything gets a little weird and esoteric, because not everything is going to be so obvious and like fit nicely with the statements that we had up top, which is too bad. All right, P or Q is going to be true, and also P or not Q is going to be true. So that means that the conjunction between those is also true again. All right, P or Q is true, whereas P or not Q is false. The conjunction between them is also going to be false, because now not both of them are true. And that last one, P or Q is false, and P or not Q is true. Again, same deal as the previous one. This is going to be a false statement as well. Now, this particular setup, we have true, true, false, false. We have not seen this before. So this appears, at least at the moment, to be a unique setup, to be something that we have never seen before, and this might be the easiest way to get this combination of compound true-false statements from the given ones over here. Now, I did tell my students that it doesn't actually matter what order in which you write the truth and falsehood of P and Q, provided that you're using all four possible combinations, so that it's like a Punnett square. So you have to have a true true, a true false, a false true, and a false false, right? 2 letters, 2 combinations. You're going to have 4 possibilities. Oh, yep, actually it's identical to P. No, that makes complete sense, right? Yep, that does make complete sense. So this is equivalent to just P. Yep, you got it. I wasn't paying attention to the first statement. I was just paying attention to all the subsequent ones. So this is something that you got to watch out for. Good job. Thank you. So again, one of the ways that we could have done this was we could have said, well, what would happen if we did a Venn diagram to represent to represent each of the statements. So here, what we typically do is, first of all, we call the entire rectangle that goes around the Venn diagram the universal set. So everything has to be somewhere inside of the rectangle. Doesn't matter where, but somewhere. All right, this statement on the left is going to represent P, and this statement on the right is going to represent Q. And anywhere that it is true is going to be shaded in, or anywhere that we have an element of that particular set. It depends on how you do it, but really the organizational technique works for just about anything. All right, so if we just want P, then that's going to color in everything that is in the set of P with no consideration to everything else. Boo. All right, don't do that. Stay within the lines. The lines are your friends. All right, so anyway, this is just P. Naturally then, if we just color in the Q one, that's just Q again. And then if we want the left side here, P or Q, we're going to accept everything that is in P and also everything that is in Q. That's going to be all of this stuff here. Everything in P and also everything in Q. this one's going to be P. Nope, the other one. Not what I meant. All right. What is going on? It's not what I meant to do. Oh man. All right. Back to 100. Uh-oh. There we go. All right. So P or Q is going to be this set here. We've shaded in everything in P and also everything in Q, and that gets us this nice, you know, both circles shaded in. There's still the stuff that's outside here, which are nobody, right? Nobody belongs to that particular group out in here. Everybody is either in P or in Q. All right, so this is going to take a little bit of it's going to take a little bit of drawing, but again, if we do P and Q as possible overlapping sets, we have the universal set around the outside, and then we want to do not Q. All right, not Q is just everything that is outside of Q. That I'm in the way. Okay. All right, not Q is everything that is not in the circle for Q. So we probably should just put like Q. Stop. All right, that one's Q. That one's P. And again, here, everything that is not specifically in Q is going to get shaded in. So we take Q and we just shade outside of Q. This would be a bit better with a stylus, because then I wouldn't worry about going over the lines and stuff. It's fine. So now if we look at P or not Q, thank you, you're very kind. So if we just look at P or not Q, then we're saying we want not Q, which is everything outside of Q, and we also want to include everything that's just in P. Which means that we're also going to include the stuff that's in the intersection of P and Q in here. So this is the stuff that is in Q alone. Or sorry, not the stuff that is in Q alone. So P or not Q includes the intersection between the two, and it includes everything outside of Q entirely. Which means now that if we look at P or Q here, and then P or not Q here, we want to be able to look at what is the intersection between them. So that's our intersection here. So again, if we're going to look for the intersection of these things, or if we're going to, and this and that, then you look at the overlap between those two sections, overlap between those two graphs. Well, all of Q alone is being excluded here. So on our final answer, all of Q alone must also be out. Then here, the rest of the universal set is being excluded, whereas here it's being included. And if it's a conjunction, we only want where they both have things there, where they overlap each other. So that means the stuff on the outside of the circles is also out, which leaves the only possibility, everything inside P for both of these. So whether that is tell I'm drawing with a mouse. So everything in P, whether that is part of Q as well, does not matter. So everything that was part of P is being included in both of these circles. So now we just get P. Again, the how you'd want to label it technically is this. All right, and again, this was just equivalent to just P by itself. Boop. Okay. So, how are we doing? Yeah, these are very big on visual proofs, doing Venn diagrams. And it's really helpful for this class in particular because these are basically all liberal arts majors who are not going anywhere else in mathematics except right here. Like this is the end of the line for most of them. So, I've got to make it good. Got to make it count so that they can understand, like, oh, maybe this stuff is actually helpful, if not necessary, to something in their lives. So, we'll see how it goes. Yeah, well, I mean, most of them have been taking, like, developmental courses throughout their college years. So, it's possible for... Yeah, so it's very possible that, like, you know, they've been in math for the last, I don't know, 2 full years of their college experience, and this is the end of the line. It's also possible they're coming straight out of high school, so you know, your mileage may vary. Alrighty. Well, if anyone has any other like specific questions, feel free to ask. Other than that, I'm going to start looking for a raid target. Jason Charles Miller is up for whatever you want Wednesdays. We got some FTL Final Fantasy Fortnite. Sounds about right. I think, you know, quaternions are usually, at the very least, mentioned in Linear Algebra 2. Maybe not, like, you know, fully explained or whatever, but I'm gonna have to watch that again, because, yeah, I haven't watched his videos in a while. Realistically, I've been kind of waiting for some of the newer stuff to drop, and he hasn't done it quite a long time. There was an update sometime in the last year, but it wasn't. I think it was on the toolkit, so SDK on four-dimensional toys. I have not heard of Hyperbolica. I can imagine from its name what it probably is about. Non-Euclidean adventure in hyperbolic space. Oh yeah, this could be really messed up. Hmm. Possibly also slightly similar to Superliminal. In that there's weird geometries going on. In that case, it's a little more like, you know, your perception becomes reality rather than an alternate type of space, but that could be interesting. Let's just add that to the wish list there. Really? Okay, whatever. Well, we'll just do that in a minute. All right. So I think I'm gonna head over to Jason Charles Miller and listen to some awesome music. I'm not on the right screen. There we go. Yep, I ended up picking up Manifold Garden at some point. Did I just screw that up? Yeah, it totally disappeared, didn't it? Cool. I clicked somewhere that was not on the box. Okay, let's try that again. So, thank you everybody for coming. If you have more mathematical type questions, let me know, and I will try and find answers for you. It's nsimplexpachinko@gmail.com. And in the meantime, I am trying to get a few more people to come in and watch the streams so that maybe someday we could make a run at affiliate and show people that, you know, it's not just games on here on Twitch. It can actually be educational content too. So I know that there's other educational content, but you know what I mean. At any rate, thank you so much, and see you hopefully on Friday for games and or other Wednesdays for mathy type stuff. So this is Obi-Wan Pez for NSimplex Pachinko. Have a good night.